Hey everybody, in this video we're going to do the work with lifting fluids problem. I started to talk about it in class, so I want to do this video with a proper example. In class I outlined what some of these things are, but let's go through the example. So we have a tank that is the shape of an inverted circular cone with a height of 9 meters and a base radius of 4. So we have it is 9 meters tall and 4 meters at the top for just the radius. So that means the diameter will be 8. So think of it like those little paper cone cups that you get when you go places and to put water in them, water fountains. So kind of like that. So that's what an inverted cone looks like. So we want to know, find the work required to empty the tank by pumping all of the water to the top of the tank. The density of water is 1,000 kilograms per meter cube. So this is kind of what I was saying. If you imagine that you're putting a straw here and then you're taking water out when you sip, every time that you take a sip, it's not like a chunk of water gets taken out randomly, right? So the cross section that it makes, because the cup or the tank is circular base, as the water level goes down, it maintains that circle throughout as you go down and down the cup or tank. So in class, we talked about the work for just a strip of water. So if I take a random strip of water here, the work is force times displacement. And force is mass times acceleration. So we'll call it G for gravity, and displacement is D, the distance that has to travel out of the tank. Since it's being pumped to the top of the tank, it's going to have to travel a distance upwards. And mass is density times volume. And then we have the gravity, and the displacement, D, is the distance out of the tank. So we are given the density at 1,000 kilograms per meter cube. Volume is the area of the base, so the area of the cross section, so in this case it's a circle, times the height. The volume of any solid is the area of the base times the height. The height in this case is our delta y, assuming that I'm using the y-axis as the vertical. So that's what that dy is. And the d, the distance out of the tank. So that's the work for just lifting one strip of water. So what about all of them? Since the tank, it says, is filled with water to the top, so that means we have strips of water that go all the way up and down the tank. So the total work is the integral from the bottom of the tank to the top of the tank. So the total work is the integral, and I should probably say not from the bottom of the tank to the top of the tank, but from the bottom of the liquid to the top of the liquid. So if the tank wasn't full, then we would just go to where there's liquid. So it will be from A to B, and then the density. Density usually is given the little rho Greek symbol times the gravity times the area of your cross section times the distance out of the tank times dy, or dx if you choose to label your axis dx or your axis x. So let's see what this all looks like then. So what I'm going to do is I'm going to say that my y-axis goes from the bottom of the tank towards the top of the tank. So I'm going to call this my positive y-axis, and I'm going to put my 0, 0 at the bottom of the tank. So depending on where you put your 0, 0, that changes how your integral looks. So if you put 0, 0 at the top of the tank, that's going to change how your integral is set up. So I'm going to start with 0, 0 at the bottom, and then I'm going to show you what it looks like if we put 0, 0 at the top. And so that means that since the tank is full, we're emptying the entire tank. So my integral is going to go from 0 to the top of the tank, which is, since the tank is 9 meters tall, it will be 0 to 9. We know the density, and we know gravity. Oops, I forgot the gravity over here. And the area of the cross section, well, the area of the cross section, what is this? This is a circle. So the area of a circle is pi r squared. And then the thickness of that is our dy, delta y. So I already have that incorporated in the integral. So what we need to do then is find r in terms of y. So that we can put it in here. So my area of the cross-section, right, if I right now just put pi r squared dy, that doesn't, I'm not going to be able to solve that integral because I have two different variables. So we have a cone, and I have some dimensions. I have 4 at the top, 9 meters tall, and I know that this is the radius of my disk, of my circle. And how high is this? So this is going to be this distance, which since this is 0, 0, we are, and look at this little red marks, we said these are all possible, these are little strips of water that are going to come out of the tank. So this is just a random distance y, right? We're along the y-axis. We don't know how high this is, so the y value keeps changing as we move along the tank, so we just call it y. So we can use similar triangles in here. So I'm going to draw our similar triangles. Bear with me here. Okay, so we have our triangle, and we know this is 9 meters tall. So that side is 9. This is 4 at the top, and we have, looking back at our cone here, we have the radius and we have how high that little strip of water is. So this is r and this is y. And so this is where we have our similar triangles, right? We need to have two angles for the triangles to be similar. They both have a right angle and they share that bottom angle. So I can say then, what can we say? We're trying to solve for r. So I'm going to say r is to y as 4 is to 9. And so r equals, multiply both sides by 9, 4 nines y. So that is r. So now back on our area here, so we said find r in terms of y for our circle. So now I can say that it is going to be pi r, so 4 nines y squared. So going back to our work integral, I'm going to have, since we're emptying the whole tank, is from 0 to 9, the density of water is 1,000 kilograms per meter cubed. The gravity, acceleration due to gravity, is 9.8 meters per second squared. The area of the cross section, so that's where this comes in, pi r squared. So the area of my cross section is a circle with thickness. We already put the thickness here. That was from the volume. So we just need the area of the cross section, which is pi r squared. So pi times 4 nines y squared. So that's the area. The distance out of the tank. So the distance out of the tank is, if this is y, this is the distance that it has to come out of the tank. So what is that? So the whole thing is 9. This is y, so this must be 9 minus y. Let's go back to the cone and see if that makes sense. So here is the strip of water at this level y, some random distance y from 0, 0. And so the distance that has to come out of the tank, because we're pumping water to the top, that means it has to come up this distance. The whole thing is 9, and this is y high, so it has to come out 9 minus y. So that's the distance out of the tank. So 9 minus y, 0. And so let's gather our constants. So 0 to 9, I have 1,000 times 9.8 times pi. When we square this, I get 16 over 81 times y squared times 9 minus y dy. Now all of this over here is a constant, so we can take it out of the integral. And so I'm going to do that. So I'm going to have the work is equal to, and when you multiply this all out, I did it on my calculator, I got 156,800 pi over 81. So I didn't fully do it out of my calculator. And you're left with the integral from 0 to 9 of this. So this would be 9y squared minus y cubed dy. And now we can solve. So integrate, so I'm going to keep this crazy looking constant here. You could multiply it all out. I don't want to lose significant digits just yet. Right? I don't want to approximate too early. So when we integrate, this becomes 3y cubed minus y to the 4th over 4. And we're going from 0 to 9 because we're emptying the whole tank. So 156, 800 pi or 81. Plug in the 9. So 9 cubed times 3. I got 2187 minus, when you do y to the 4th, so that's 81 squared divided by 4, 164, oh sorry, 1640.25. And then when I simplified this out, so I did this number in my calculator, divided by 81, and then multiplied by the 156,800, I got 105.8400 pi. And this is work, so, and everything was in meters, so my units are joules. And so this would be my answer. In WebAssign, you may be asked to put it in scientific notation, so then you will multiply this by pi, so 3.14, and then try to write it in scientific notation. But on a quiz or a test, if you just leave me this will be fine. Okay, so I did say that what about the other setup? Where you place your 0 matters. So let's try, what does it look like if you place the 0 at the top? So let's go look at that. Okay, so if we do the same problem, so this is still 4, the radius is 4, and the height is 9. Now, the difference is, what if we place the 0, 0 at the top? How does that change the setup? Now, the work should be the same. It's the exact same tank with the exact same amount of water in it. So we just want to know what is the work. So the work should be the same. Our setup is going to look a little different just because we place our 0, 0 somewhere else. And so the work, I am still going to have the integral, the tank is still full, so from 0 to 9, the density is still 1,000, the gravity is still 9.8. The area of the cross section, so we still have a circle, right? So the area here is still a circle, so the area is pi r squared. So now does that change? Let's look at our similar triangles and see how that changes now that the 0, 0 is at the top. And mainly because 0, 0 is here. Let's see, so that means we probably want, so this also kind of depends. Do you want this to be the positive y-axis? I usually tend to want to work with positive numbers. So I would call this the positive y. So that means that this distance here now is y, and this is, right, this would be the 9. So this distance here is 9 minus y. And so that does change things because our similar triangles are going to look different. So how does our similar triangles look? Okay, so the main difference is going to be that now notice that my r didn't change. So r is still here. Oops, I meant to do that in red. R is still there, but as before, because we had 0, 0 at the bottom here, in the previous way we did it, that means that the distance to the strip was y, because we're measuring from 0, 0. Now, because our 0, 0 is at the top, now this distance is y, right? You're measuring from there, assuming that this is the positive y-axis. We still have, this is still r, but now this is 9 minus y. because the height is still 9. So our similar triangles, then I will say r is to 9 minus y, right? As 4 is to 9. So this side is to that side, this is 4, as the height of the triangle, 9 minus y, is to the big height, 9. And so r is equal to 4 nines, then multiply both sides by 9 minus y. And this is my new r. And so that is going to change the setup over here, because now I'm going to have the area of the cross section is pi r squared, but my r is different. It's 4 nines, 9 minus y, quantity squared. What else has changed? The distance out of the tank is now y. So I have density times gravity times area of the cross section times the distance out of the tank is y, and dy. And so when we pull all the constants out, right, I'm going to have 0 to 9. I still have 1,000 times 9.8, the gravity times pi, and this is still 16 over 81, but now I have 9 minus y squared times y dy. Pulling all the constants out, we will get the same constant that we did up there, and now this is going to be a little bit different. So the work should be the same, but I just wanted to illustrate how the setup looks different depending on where you put your 0, 0. Okay, so I hope that that is helpful. I'm going to record another video to do something that where the cross section is not a circle.